All right, well, I'm going to tape a short lecture for you guys. As you can see, it's nighttime. I think I want to do it today so that you have the backing for the material of homework number 10 that I just posted. So this lecture is going to have, let's see, a significant component has to do with structural dynamics, and so I have to step back because there are a number of people in the class that have not had structural dynamics, and of course although I don't need to present the material so that you can execute complicated computations, it is essential that it be understood what the concept is. I'll try to make it also so that for those of you that had the structural dynamics class, it would still be of some interest. So let's begin. Okay, no, let's not begin. Let me just say where am I going? Where I'm going is to continue the discussion from previous time, which is when we do system identification, it is not the case that you're going to have this huge eigenvalue gaps, singular value gaps when you look at the singular value decomposition of the Hankel matrices. So the selection of the order of the system is never so obvious, of the order that you should use, nor is it possible always to know, to have clean results with regards to the distinction between eigenvalues, frequencies, and mode shapes that are of the physical system and frequencies and mode shapes that actually respond or exist due to the noise in the data. Okay? And I believe that I gave you guys two criteria to distinguish computational modes from physical system modes. One was the fact that the damping cannot be very large, unless it's a very special structure with some added dampers and things like that. The damping is small. So when we calculate system ID, if we find that the damping is 10% or something like that, then we assume that that is a computational mode. The other reason is that if the mode appears to be strongly complex, we also discard those modes. I gave you an index of how the modes, how we can quantify the modal collinearity, right? And I don't know what I called it, but it could have been, for example, the modal collinearity index or whatever name I gave it. And it was simply 1 divided by S2 over S1 times 100, right? And it's in percent. And that S2 and S1 is such that if you take the mode, right, you take the real part and you make it as the first column of a matrix, and you take the imaginary part and you make it as the second column of a matrix, and then you take the singular value decomposition of that matrix, and that singular value decomposition will have two singular values, S1 and S2, and they are these, right? If the singular value, if S2 is 0, that would be the ideal case where the modal collinearity index is 100% and the mode is perfectly real. If the modal collinearity starts getting to be smaller than about 85% or something like that, we tend to believe that the mode shape, that mode is probably computational, not part of the physical system. There is, however, and here is where I left it last time, there is an exception, and that exception is that, as we will see, sometimes it is possible for a mode to have a significant imaginary part, and that usually happens when the eigenvalues of that mode that you're looking at has another neighbor that is close. So I was thinking last time to actually give you the full presentation of the derivation, but eventually decided against it because it was very long. So I will just give credit to Lord Rayleigh, which is the person who derived this expression the first time. So Lord Rayleigh showed way back, right, way back, that if you have a complex mode, that complex mode, and I guess I should have started, well, I don't know, this is the order it came out. If you have a complex mode Cj, the jth mode, that mode could be approximated as the mode from the system without damping, which is real, plus an imaginary part, which is the summation from K1 to J, no, not to J, from K1 to N, right, of omega J C K J omega J squared minus omega K squared times xk. Now, I will make some sense of this formula for you a little bit later, even more, but let me just try to give you a feel, well, an initial introduction to it. If we have a complex mode, the third one, Z3, we would say, according to Raleigh's formula, that C3, that complex mode, is probably something like the third real mode that we get from K and M, and it has an imaginary part that is approximately going to be, the whole thing is approximate, but anyway, it is something that I would have to talk about this, but this xk are the real modes 1, 2, 3, oh, of course, and this is for K not equal to J. So you don't have to use, if you're doing this third, you don't have to do the third here. But I know it's going to be confusing, so I probably should not dedicate much time right now on this. I should take it at the end again. But let me just say for the first, right away, that the key aspect is this denominator. Because you see you have omega j squared minus omega k squared, right? So if omega j and omega k, for example, let's say that j is equal to 3, so you're looking at the third mode, right? And then we're looking at k being 4. So this is if omega 3 squared minus omega 4 squared, right? If these two frequencies, if omega 3 is close to omega 4, then what's going to happen is that this difference is small, right? And if this difference is small, this coefficient can be large, and a large coefficient here means that the imaginary part of the mode can be significant. Under most circumstances, if the frequencies are not close, because this numerator tends to be very small, then this term is not important, and the modes, the complex modes, tend to be essentially the real modes. Now I know that for those that, or for anyone who has not done the structural dynamics, that can be very confusing. So let me try to do an effort to unconfuse it. Maybe this would have been a better order, but since this is taped, it's fine. You can always rewind and replay, right? So let's say if we have no damping, okay, if we have no damping in a system, then we say that a mode is something like this. K times phi j is equal to m times phi j times lambda j. Okay, so that's a mode. Notice that if we have no damping, damping is irrelevant, right? All we're saying is that a mode is such that if you multiply it times the stiffness matrix, you get something. And if you multiply it times the mass matrix, you get the same thing except for multiplication by something. And that something is the eigenvalue, right? So, this is the standard thing that 99% of the time people use in practice. They talk about modes, they are talking about the modes for no damping, okay? Or what is equivalent for classical damping that I will mention in a little bit. So that's no damping, right? Now what if there is damping, as there always is? So if there is damping, the equations are, the equation that you have to solve to get the modes is this. Okay? M times lambda squared plus the damping times lambda plus K times phi is equal to 0. Now, if the damping is 0, this would be m times lambda squared plus k equal to phi. And that's really just the same thing we had before. In fact, let's see, what was it that I wrote it? I wrote k phi is equal to m times phi times lambda was the way that I had it, right? So that's this can be written as m times lambda minus k parentheses multiply times phi is equal to 0, right? So you can see that in this particular case, where there was no damping, we don't get exactly, I mean, you see the parallel, but it's not identical, right? No, it's not. Now, what happens is that with damping, I mean, without damping, this lambda is really omega squared. And with damping, this lambda is really not omega squared, but is equal to minus omega times the damping ratio plus omega times 1 minus the damping ratio squared times the identity. So they are related, right, because they both have omega, but they're not really the same thing. So if, of course, we came here and we put no damping, then what we would have with no damping is that the real part would be 0, right? And then this part would be 1, and we would have that with no damping in this version, lambda is omega I, right? Lambda is omega I. So what would be lambda squared? Lambda squared would be minus omega squared, right? So if you put it here, you would get minus m times omega squared plus k times phi equal to 0. And you can see that that's the same thing as we have here, because this is m times omega squared minus k times phi equal to 0. And since I can just multiply times minus 1, that's the same thing as saying minus m omega squared plus k times phi is equal to 0, right? Which is the same as we have right here. All right. So, once again, without teaching this whole structural dynamics class again, or teaching it now because it's not possible, I will summarize here. No damping. No damping. We have k times phi is equal to m times phi times, actually, you know, maybe this will help keep the thing, m times phi times omega squared, maybe, in the case of no damping. In the case with damping, the eigenvalue problem is m times lambda squared plus c times lambda plus k times phi is equal to 0. Okay? So this is the case of no damping. This is the case with damping. Now, there is one, okay, in the case of no damping, phi is real. Or it can be normalized to real. There's no need for imaginaries. In the case of with damping, this vector, this eigenvector, in general, has a real part and an imaginary part. That is, in general, the eigenvectors with damping are complex, not real. Maybe I will stop for a minute and indulge in trying to give you a little bit of a physical feel. At least those in the dynamics class probably already did this, but let me just compare the two cases. Imagine that you have a system with two masses. And let's say that we have the first mode that looks, let's say, like this. Okay? And let's say this is A and this is B. Then and this frequency is omega 1, which is the same thing as to say F1 or period 1. So you have this mode. Now, what does it mean? It means if you put the structure in the position AB, and that's a mode, solving from here, and you let it go, this structure will just go back and forth. Boom, 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 and it'll maintain that shape. That is, if you film it, that's what you see all the time, right? So this will go minus A, minus B, and it just repeats and repeats and repeats. Now, that condition can also be illustrated like this. If you were looking from, let's see, how did I do that? No. You can also illustrate it by saying, you can sort of illustrate it this way, right? You can say that what you have is a vector of length A and a vector of length B, which are exactly parallel. B is longer than A, right? And they are rotating together with a frequency omega 1. So when they are on the horizon, imagine that what you actually see is the shadow. So if you have the sun coming down, the light, the shadow of the B would be this, the shadow of the A would be this. When the vectors are on the horizontal axis, they have the maximum shadow. So that's when this thing gets to maximum response, B and A. They rotate together, and when they go through 90 degrees, A and B are like this, right? And that's when the structure goes through 0. And then it goes to here, and now you have them on the negative side, with A here and B here, right? And then they rotate like this, and it's back to 0, and then back to the right side, and so on, right? So what we have on the normal case can be viewed as vectors like this, which are rotating at the frequency of the mode. In fact, if we were to look at not the first mode in the two-mass system, but let's say at the second mode would be this mass going to the right and this mass going to the left. So that could be A and B, and the frequency would be omega 2. In our circle idea, we would say that A is like this and B is like this. And they are rotating with a frequency omega 2. So when they are in the horizontal axis, A is giving 3 o'clock on the clock, right? And B is 9. And so you would see this A and this B. Actually, I should have made this a little bit bigger to saturate like that, right? So you would see this A and B. It rotates, they both go through 0 at the same time. That's when the system gets back. Then they go change flip sign, because this goes here and that goes there. And the system is now like this, right? And so on. So the point is that the vectors are aligned with each other. They are either in the same direction or they are 100 degrees opposite. That is what happens when you're talking about real modes, okay? And those are easy to visualize. Now, in the case of a complex mode, when there is damping in general, we can still view the situation in terms of vectors. But what happens is that, well, it's easier to show on the sketch. Imagine that this amplitude was A on the mode, and this amplitude is B, like we had. But what happens is that they are now not in phase. So we would say something like this. A, right? But B, instead of being together with A, B might be here. And they are both rotating, let's say, with omega 1. So what happens is that A and B do not get to maximum at the same time. Because if you put A at 3 o'clock, B still has already passed, right? And as you go rotating counterclockwise, B will get to 0, that is, the shadow will get to 0, and then A still hasn't gotten there, and so on, right? So when you film a structure that has not a complex mode, vibrating in a complex mode, you don't see the same shape all the time, because the projection of these vectors as they rotate on the, I'm using this analogy of the sun hitting this thing and looking at the shadows is what you see. But this thing that you observe will not be the same as time passes. But if you wait one period and you actually photograph the stuff every period, you will see the same thing, right? Because it's not that there is anything different than before, it's just that the vectors of the amplitudes are now out of phase. So they could all be in the same direction with an angle, or they could be in different directions with some angle. Now, consider, for example, a situation where you have a complex mode that is like this. Right? So A and B. So even though B is not really aligned with A, the difference in the angle is not very big, right? So we suspect that this complexity is not strong. So we would refer to this as weak complexity, right? As opposed to a situation where A is like that, and and maybe B is like this, right? So they're still rotating, but they're really not even close to in line, right? Or out of phase. So this is high complexity. And this would be low complexity. Now, in this case, low complexity, 1 minus S2 over S1 times 100 is probably going to be 92 or something like that, right? In the case of high complexity, where one amplitude is like that and the other amplitude is like this, they're way out of phase. There could be more than two, of course, I'm just using the two mass. This would be high complexity. And in this case, I don't know, I'm just making these numbers up, but if we were to calculate this index, maybe we would get 70 or something like that, right? Now, we would tend to call, if we are doing system ID, we would tend to say that it's probably physical, but this is probably not physical, because we do not expect such high complexity in physical systems, unless the modes have close frequencies. Okay? If the modes, or not if the modes, if a mode has a neighbor whose frequency is very close to that one of itself, then that mode, the damping can shift it around significantly. Okay? So, let me see. Okay, there is something called classical damping. And classical damping simply is the kind of damping that does not affect the fact that the modes will still be real. The modes are the same. As if there was no damping. Okay, so classical damping is the same as if there was no damping. Now, real structures, okay, real physical systems, if you want to be strict about it, never have classical damping. Classical damping is like a dot and you have a map, a plane. So it's a point, it's not dense. So the likelihood that your structure has classical damping is basically zero. Now, notwithstanding, the model of classical damping is used all the time. So we normally assume that the damping is classical. Is it because the damping is actually classical? No, I just said the damping is never classical. It is because the assumption of classical damping simplifies computations significantly, and the error that it brings is very small, except for special cases. And at this point, I go back and emphasize one more time the expression. So if phi, actually I use z, so maybe I should stick to the notation. If zj is a complex mode, then Lord Rayleigh showed that that complex mode would be the same as the mode with no damping, or classical damping, right? Plus something that has a denominator which is omega j squared minus omega k squared. Okay? And over here multiplies all the other modes. And this is omega j times ckj. And this summation is from k equals 1 to n, where k is not equal to j. That's the second time I put the formula. Let's see, what else can I do to help you follow that one? Okay, yeah, there's one thing I can do to help understand. And it's this. I want to give you a feel now for what is ckj. Okay? So, if we have a damping matrix, which is C. Okay? And the mode shape, let's say that the undamped mode shapes are that symbol. Okay? And all of them is this. Then phi transpose times the damping matrix times phi, if that is diagonal, then the damping is classical. Now I know this can be quite confusing because you don't know what do I mean if it's diagonal, what do I mean if it's a C, and so on. The point is, all this stuff is basically theory because in practice we don't really know the damping matrix. We can calculate the mass matrix by knowing how much things weigh and this kind of thing, right? And we can calculate a stiffness matrix by knowing what is the modulus of elasticity of the material and what is the moment of inertia of the cross-section and all of that. But the damping matrix, we really do not calculate it from physical properties. We specify it. And that is for doing forward modeling, right? Not system identification. But to do forward modeling, we specify the damping, and we tend to specify the damping such that the mode shapes of the undamped system will make this product diagonal. If that is true, then a bunch of things get easier in structural dynamics, and we call those matrix classical. Now that puts us into this formula. If the damping was not classical, then what happens? What happens if the damping is not classical is that these terms are not zero, right? So let's say, for example, that this was a 3 by 3, otherwise I get confused. So if it was a 3 by 3, this would be like this, right? So if I have a damping matrix that is of a 3 degree of freedom system, if the damping was classical, there would only be, once I do phi transpose C phi, I would only have numbers here. If the damping is not classical, then there would also be numbers outside. Okay? The numbers that are outside when I do this are these. So if we are looking, for example, at the mode shape number 3, let's say this is 3 by 3, I'm looking at the third complex mode, then this says that this would be equal to the third real mode, just using K and N, plus, right? Then I would come here and say, what am I doing? I need to do omega, my J is 3, right? So I need to take omega 3 and multiply it times what? Times CKJ, right? Now K is 1, so row 1, column 3. So row 1, column 3. So that would be C, what did I say? Yeah, C13, right? So that would be right here, C13. And then I'd have to take the other one and the other one. So okay, plus omega 3 times C23, right? Because K is not equal to J ever. So that sum, wait, no, my error, sorry. So little space. Okay, so C3 is equal to X3 plus, the first term here would be omega 3 times C13 divided by omega 3 squared minus omega 1 squared. And then what is this? This is x1, right? So this is a coefficient times x1. Plus, then the next term would be omega 3, multiply it times C2, 3, right? So that's second row, third column, that would be this one, C23, right? Divided by omega 3 squared minus omega 2 squared multiplied times x2. And that would be it, right? So that, oh, and of course this is times I. So this is that times imaginary. So the thing in the brackets here is the imaginary part of the third mode, more or less. The bottom line, or at least the point I've been trying to hopefully make halfway clear, is that these terms, if omega 3 is much bigger than omega 1, that thing is big, C13 tends to be small, that is just not very important. And in general, as long as these two things don't get close, then these terms are not very important, and we do not expect the imaginary part of the complex mode shape to be significant, so we can normally neglect it. The exception is if it turns out that two frequencies are close to each other, right? So if anything stays with you from this discussion, is this. If anything stays with you, what I want to stay with you is the following. Mode shapes are nearly real, except in cases where omega, where the eigenvalue gap, which is the distance between two omega squares, is small. So, when you are doing system identification for damage detection, or for whatever we're doing, or for model updating, for whatever it is, when you're doing system identification, we use the model collinearity index to eliminate modes that we think are no good. And if the model collinearity index is, let's say, less than 80%, we can safely say the mode is no good. But watch out, except that you cannot say that if it turns out that that mode has another frequency that is very close to it. If it has another frequency, if the adjacent frequency is very close to it, then that might be a truly honest complex mode, okay? In that case, the model collinearity index is no longer useful, because the model collinearity index is just trying to say, hey, we know that these modes are not complex, they're just real with a little bit of complexity most of the time, but not always. If that would be the same thing as saying, we know that the damping is small. Yeah, the damping is typically small, but you know, not if you have a structure that you've added a bunch of dampers, mechanical dampers and so on and so forth, and it's got, you know, brick masonry and all kinds of stuff that could make the damping be 8% or 9%. So if you are dealing with a special situation, you cannot say that a priori you know that the damping is small, because it's not small in that case, or a priori that the MCI, model collinearity index, is large, because wait, it could be small because two frequencies are close to each other. Okay, so that is a simple, well, not as simple, but that is as summarized as I can come up with. For the purposes of this course, and your ability to perform system identification correctly, okay, you are going to say this: when I perform system ID, I have my singular values of the Hankel matrix, and I may not see any gaps. no clear gaps. I can tentatively select an order. Once I select that order, in this case 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, say 12. Once I select that order, in this case 12, that means that now I can get my A matrix, my C matrix, and then I can get my eigenvalues, my dampings, and my model collinearity indices. Since they come in conjugate pairs, I may say 1 and its pair, 2 and its pair, 3 and its pair, 4 and its pair, 5 and its pair, and 6 and its pair. And then I might say, okay, damping ratio here, model collinearity index here. And we did this last time. And you might say, okay, I don't like this one. Model collinearity is too low. So we get rid of it. I don't like this one, the damping is too high. And so I am left with the fact that I was able to identify 3 modes that have low damping and high model collinearity indices. Okay? Now, to conclude this short lecture, what I said is that one thing that is kind of unsatisfying is that in order to do this process, we made an arbitrary choice that the order was 12, right? You wonder, what if I had taken 14? What if I had taken 16? And so on, as I think I said last time. So the state of the art presently is to not make a selection of the order, but to make many selections of the order. So imagine that you select order 1, 2, 3, 4. I mean, you don't have to select them all, or you don't have to select them in order, but you could go like this until order, something, 30. So this one has only one eigenvalue, this one has 2, this one has 3, 4, 5, 6, 7, etc., right? As you go, each one of these things, let's say this one of order 4 gave us, this 4, and this one of order 30 gave us 30, right? We can apply the criteria that we only take low dampings and high modal collinearities. And we could apply that criteria in every one of the orders, right? So a stabilization diagram is simply a plot of which poles, which frequencies we keep versus the order. So, as I think I drew last time, we put the order here and the frequency here. So it may be that I don't see this frequency at all until this order, but once I get to this order, I see it all the time, right? From this order to this order, I see this frequency with little variability all the time. So that frequency looks pretty good. Now over here, there may be one that shows up over here, and then it shows up again, but then it disappears. So, you don't have much confidence, or it appears here and then, there, or something like that. So this frequency, it seems like it's probably more noise than anything else. So we refer to a stabilization. Now, of course, in our case, each one of these points, which is a frequency, already satisfy that the model collinearity index is greater than whatever we decided, greater than the threshold, and that our damping is less than the threshold, right? So the points that we are plotting are already cleaned out. What we want to see is not who's good and who's bad, but we want to see who gets repeated no matter what the order that we choose. And that's a stabilization diagram. Now, I have posted for you in Blackboard a program that generates the stabilization diagram. The program also uses another one that is called order polls, and I've also posted it. And I posted homework number 10, which is to repeat homework number 8 with the help of the stabilization diagram. Okay? You will have to do something yourselves, which is not something I just wrote the code for. You have a program to do ID. What do? Output only. When you're doing output only identification, what do? You take the output data, and from the output data you run the program stock or something like that, which computes Markov-like parameters, right? Let me just say Markov parameters. Markov parameter, right? Like, right? Then what do we do that? After we have this Markov-like parameters, we run Hankels, right? And from those Hankels we get H1, H0 and H1. And then at that point we decide an order, right? And then we run the program ERA. That gives us our A1 and our C1. So what you have to do is you have to put this in a loop and change the program here. Well, you can change it or leave it the same depending on your expertise in programming, meaning instead of asking it to show a figure and you select the order, you could just say select order to be equal to J, whichever way you want. The point is that once you do this for loop, you should have A1 that comes out of here, but not one time, but in a cell. You should have A1, 1, A1, 2, A1, 3, etc., right? All of these A1s are for different orders, okay? And you should have C1, 1, C1, 2, C1, 3, etc. for different orders. They should be in cells. The program stabilization diagram takes this A1 and this C1 cells as its basic input. Plus, it's obviously explained in the commentary the threshold that you want for the damping and the threshold that you want for the model collinearity index. Okay? So I put the deadline for this on this Friday because, you know, time is moving along, and I'd like you to try this soon, because it doesn't matter how much I try to explain here over and over, your ability to understand, or not understand, to get a grasp of how to run this thing can only be acquired by you sitting down and trying it, right? So I'd like you to try it as soon as possible. Download the code, stabilization diagram and order polls. Take your data from homework number 8. Don't go crazy at the beginning by losing too much time trying to do these loops or something. You know, you can just try, I don't know, 5 or 6 orders by hand. Just run the program 6 times with order 4, 6, 8, 10, something like that. Then create these A1C1s and put it in the stabilization diagram and see that you can get something. Once you see that you can get something, then you can refine it. Make a good loop, and then you can do many orders and so on. And this should help you to decide on which ones are the good modes and which ones are noise modes or computational modes. Okay? All right. So we'll call it a day on this one here. Hopefully you'll be able to make up with your ability to look at MATLAB codes and figure it out.